So a little bit of lecture theory about Markovnikov. But first I'm going to tell you that I don't really like to call it Markovnikov. I like to call it Marky Mark, the Marky Mark reaction. And this is because I really probably couldn't pronounce Markovnikov back into the day, and no one knew what I was trying to say or talk about. So I gave it a nickname, and being an 80s kids, well, Mark Wahlberg came to mind. And we have Marky Mark that came onto the picture during that time. So Markovnikov kind of looks like Marky Mark to me, and that's just kind of the nickname that I gave it. So we're going to talk about the Marky Mark reaction, or Markovnikov. And in the previous videos, you often saw me come up with like this 6-membered or this 4-membered carbon chain. And I said this really only deals with unsymmetrical molecules, and it has to be an alkene or an alkyne. And in those videos, I basically said that the double bond will get broken. So we're going to erase that, and we're going to put 2 things on to that carbon. Now, the only thing I want to do for a minute is just to go through and kind of give you more of the hydrogens. So before we go any further, I'm just going to erase those bonds that I've drawn, and I'm going to redraw that double bond of where it should be, and I'm just going to go through and add the hydrogens in. So this carbon needs 2 more hydrogens onto it to give it a total of 4 bonds. This one needs 1 more. That way it will get 4. This one needs 2, this one needs 2, this one needs 2, and this one needs 3. So I'm just going to rewrite this structure for a second. It's CH2 double bond with a CH, CH2, 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 and CH3. So now, after we've added the hydrogens, Markovnikov, or the Marky Mark, will be much easier to understand. So I'm going to go through and erase the double bond. And when I erase the double bond, 2 sites of attachment open up. I draw 1 on top and 1 on bottom, not because that's the way you have to. It's just kind of generally accepted to do it that way. So that way you've got room to write these incoming groups that you might add to the molecule. They're not kind of sandwiched up together, and they're a little bit separated from each other, at least on a sheet of paper. All right, so we know that in these reactions, such as this one in this particular lab, if I have a double bond, the double bond gets broken, and we talked about 2 sites of attachment getting opened up. And we questioned, where do things add? So for instance, if I add on an H and an OH, maybe in form of water, and I bring water into the picture, well, where does the H go and where does the OH go? That's always the question. Which one is the major product? Which one is the preferred product? Because that's the one that I want to write down. It's all about predictions here. So I've got to figure out which carbon does the H go and which carbon does the OH go. Well, Markovnikov is going to help you out. And this is what Markovnikov basically said. Markovnikov said that if you have hydrogens that you are adding onto a molecule, if that's one of the choices, hydrogens are kind of picky. And hydrogens only want to play with other hydrogens. That's it, folks. That's all that Markovnikov's rule states. That's not too difficult, is it? If I have a hydrogen that I'm adding to the molecule, then that hydrogen would prefer to play with other hydrogens. Doesn't want to play with anybody else. So that means in this molecule, I have 2 choices. I have a carbon that's here, and I have a carbon that's here. That's where the bonds are. That's where the bonds are going to be. Well, I've got a hydrogen in this case that I need to add on to this molecule. And OH is going to be the other piece that I'm going to add on to the molecule. Well, I'm adding hydrogen. And Markovnikov's rule states that in most of the reactions, hydrogens will play with other hydrogens. Meaning that when hydrogen comes over here to this molecule, it will look at these 2 carbons and it will say which one has more. And it knows that this very first carbon has 2 hydrogens onto the first one, and the second carbon only has one hydrogen. That's it. So this new incoming hydrogen, I'm going to draw this one in red, is going to attach to the very first carbon because of that. That's where most of the hydrogens already are. That's where that hydrogen that's incoming is going to prefer to go, because Markovnikov stated that, traditionally speaking, hydrogens go where the other hydrogens are. It's as simple as that. So this OH molecule that we are bringing into the picture, that means that the OH molecule or functional group will have to go onto the second carbon because of that reason. This is what we call a traditional Markovnikov reaction. Hydrogens play with other hydrogens. Wherever the most of them are, that's where the incoming hydrogen is going to go. Now, I want to tell you that there are things called anti-Markovnikov. So anti-Markovnikov reactions do exist. And those anti-Markovnikov reactions go backward. That means the hydrogens do not go where the hydrogens already are. Okay? Now, there's a handful of these reactions. There's certain criteria that allow anti-Markovnikov to happen, and you'll learn about these, especially in a full-blown organic chemistry course. So the goal of this laboratory is to do a reaction with hexene, like I've drawn up here at the very top. You're going to add reagents to hexene, and those reagents are going to break a double bond, and two sites of attachment are going to open up. One of those will be hydrogen that will get added on to one of those two carbons. And it's your job to figure out if this reaction is Markovnikov or if this reaction is anti-Markovnikov in the mechanism. Now, I don't need you to draw curvy arrows. I don't need you to kind of draw out how this product is actually going to get formed. That requires a little bit more of organic information than what we're ready to talk about now, or what we can actually talk about in the amount of time that we're given. So, because of that, no mechanisms, no curvy arrows. For this reaction, you just simply want to know, is it Markovnikov or is it anti-Markovnikov? And you'll know that based on where the groups go. Does the hydrogen play with the other hydrogens, or did the hydrogen go on in the opposite location? Now, HOH is not the only thing that can make this do, right? So if I've got an H and a Br, the same thing is going to happen. I've got a hydrogen here. I'm going to add it onto the molecule. The two sites of attachment open up. If it's Markovnikov, then the hydrogen will play with the other hydrogen. So that means the hydrogen would go there in that case as well. And then the Br would go onto the second carbon because we're using HBr instead of H and the OH now. So there's no difference in how this reaction takes place and what you use. It's just basically, do you have a hydrogen? If you do, that hydrogen's going to prefer to play with others unless it's anti-Markovnikov. And that's the whole point of this lab. That's what you want to take away from the lab. You're going to do this reaction. You're going to get a product. You're going to identify the product. Is it 1-hexanol or 2-hexanol? Which one did you make? And based on the product and which one you get, you can then describe if this reaction went Markovnikov, like normal, or anti-Markovnikov, which is backward than what we traditionally see. All right? So that's kind of a very down and dirty way of explaining what Markovnikov's rule actually is. So keep this in mind, learn it now, because you'll often see this in an organic chemistry course. So it will come back again later on in a different class with a different instructor. However, I'm giving you a head start. So you better ace those tests when you get them.